Welcome dear students, we are on the CEC curriculum lecture and we are discussing the electronic components and in the series of the electronic circuit. We discussed the many electronic components up to now, and in today's lecture we are discussing the thermistors. Thermistors, thermal plus resistor that used to measure the temperature as the resistance changes. So the main difference between the thermistor and the thermocouple, we can discuss up to now that what is the thermistor and how it is constructed, and there are the many types of thermistor shape and the size of the thermistor are of many type. So now we discuss how the thermistor and the thermocouples are different. The main difference between the thermistor and thermocouple are that the thermistors are having a narrow range of the sensing, like 55 to the 150 degrees centigrade. Although this varies depend on the brand which we are using and depend on the material by using which we construct the thermistor. Next is the sensing parameter, which is equal to the resistance. Next is a non-linear relation between the sensing parameter and the temperature in the thermistor. These are the basic points of thermistor. Moreover, the NTC, the negative thermal coefficient, thermistors have a roughly exponential decrease in the resistance with the increasing temperature. So good for sensing small changes in the temperature. It's hard to use the thermistor accurately with the high resolution over more than that of the 50 degree centigrade range, and the sensing circuit is simple and doesn't need amplification and is very simple and very easy to install. Moreover, accuracy is usually hard to get better than that of the 1 degree centigrade without calibration. In case of the thermocouple, they have a wide range of the temperature sensing, like we have the minus 200 to 350 degrees centigrade. This is a very wide range of the sensing which is used to measure the temperature in any devices. Moreover, the type J is equal to 95 to 760 degrees centigrade. Type K is equal to 95 to 1260 degrees centigrade. Other type go to even the higher temperature. Moreover, can be very accurate in case of the thermocouples. Sensing parameters, voltage generated by junctions at different temperature in case of the thermocouple. So sensing parameter in that case, that is the resistance. In this case, we have the voltage that is generated by the junction at different temperature. In the thermocouple, voltage is relatively low and have a linear relationship between the sensing parameter, voltage and the temperature that we take. In the thermistor, we have a non-linear relationship between the temperature and the resistance, but in this thermocouple we have the linear relationship between the sensing parameter, that is the voltage, and the temperature. So this is the basic difference between the thermistor and the thermocouple. As per the requirement, both the devices are used in the electronic circuit. Now thermistor versus RTD. What is RTD? RTD is the resistance temperature detectors, that is also known as the RTD sensors. How it is different from the thermistor, as it is also the resistance temperature detectors, and these are almost similar to the thermistor. Both RTD and the thermistor have varying resistance dependent on the temperature. As in case of the thermistor, we also use the resistance, and in case of the RTD, we also have the thermistor. We also use the resistance temperature detector. That is similar to, almost similar to the thermistors. The main difference between the two is type of the material which we are using in the construction of thermistor and the RTD. The thermistor are commonly made with the ceramic or the polymer material, while RTD made of the pure metals. So this is the basic difference between the thermistor and RTD. RTD made of pure metals, while thermistor are commonly made with the ceramic or the polymer materials. In terms of the performance, thermistor performs better as compared to that of the RTD. Thermistors are made accurate cheaper and have faster response time than that of the RTDS. The only real disadvantage of thermistor versus RTD is when it comes to temperature range. RTD can measure the temperature over a wide range than a thermistor. So, a wide range, if we are having a wide range of measurement of the temperature point, then we use the RTD as compared to the thermistor. Aside from this, there is no reason to use the thermistor over a RTD. So, we generally use the, nowadays we generally use the thermistor in the devices. What is the difference between the thermistor and the other sensors, that is the temperature sensors? So, in addition to the thermistor, several other types of temperature sensors are also used. The most common are the RTD and the integrated circuit, also used for measurement of the temperature. What integrated circuits, such as the LM335 and 8590 types of the integrated circuit used for measurement of the temperature, and these are the sensors. And which sensor work best for a particular use is based on the manufacturer. So, we are having a comparison table, and according to the benefits, according to the devices, we use the various type of the sensors, in which we can use a thermistor also, we can use the RTD, we can use the thermocouple. So, thermistor come in a variety of the shape, as we already discussed, that the disc, chip, bead or the rod, and can be surface mounted or embedded in the system easily. As there is a lead connection on both the point, and they can be encapsulated in epoxy resin or the glass, moreover baked on a phenolic or the painted. And the best shape often depends on the material is being monitored, such as the solid, liquid or the gas, and as per the requirement. For example, here we having a bead thermistor is ideal for embedding into a device, while a rod, disc, cylindrical heads are best for the optical surfaces. You see on the screen, there are the basic types of the thermistor defined here. So, in whenever we use the optical surface, then we use the rod, disc and the cylindrical heads. Otherwise, the bead shaped thermistor generally used in the devices. These are the many shapes of the thermistors are available. Now, thermistor chip is normally mounted on the printed circuit board. On the PCB board, we mount the thermistor chip, and there are the many different shapes of thermistor, and some are defined here. These are the basic shape for the requirement. The shape can be chosen for just to get the which allows a maximum surface contact with the device whose temperature is being monitored. So, that is that the device is selected accordingly, and regardless of the type of the thermistors, the connections to the monitored device must be made using a high thermally conductive paste or the epoxy glue. So, it is usually important that this paste or the glue is not electrically conductive, otherwise it will produce the noise in the output. So, how does a thermistor work into a control system? We use the thermistor in the control system. The main use of the thermistor is to measure the temperature of a device, that we know. Then in the temperature control system, the thermistor is a small but important piece of a large system. So, how it is used in the control system? So, a temperature controller monitors the temperature of a thermistor. So, it then tells a heater or the cooler when to turn on or off to maintain the temperature of the sensor. So, there are the three main components used to regulate the temperature of the device. First is the temperature sensor, that next is the temperature controller, and third is the Peltier devices, that is labeled here as a TEC, that is thermoelectric cooler, that we will use in the controller. So, the sensor head is attached to the cooling plate that needs to maintain a specific temperature to cool the device. So the wires are attached to the temperature controller. Now this temperature controller is also electronically connected to the peltier devices which heats and cools the target devices. So the heat sink is attached to the device to help with the heat dissipation. So the job of the temperature sensor is to send the temperature feedback to the temperature controller. This temperature sensor sends the temperature feedback to the temperature controller. The sensor has a small amount of the current running through it, and that is called the biased current, which is sent to by the temperature controller operation. You see here temperature control on the left hand side, that is a cooler current, and right hand side we are having the heat sink, and tech is here, and embedded temperature sensors are attached here, and this temperature embedded temperature sensor send the feedback to the controller, and the controller maintain or control the current, or the maintain the heat sinker. And in this manner it takes the sensor information, compares it to that of the what the unit to be cooled needs, called the step point here, that give the signal that at which point the cooling will be done, and that is called the set point, and adjust the current through the uh, peltier devices to change the temperature to match with the set point. So the controller cannot read the resistance, so it must convert the resistance changes to the voltage changes by using a current sources to apply by a bias. So current across the thermistor to produce a control voltage. So temperature controller is the brain of this device. The location of the thermistor is the system affects both the stability and the accuracy of the control system. For the best stability, thermistor needs to place as close to the thermoelectric or resistive heater as possible. For the best accuracy, thermistor needs to be located close to the device requiring temperature control. Ideally, the thermistor is embedded in the devices, but it can also be attached using the thermally conductive paste or the glue on the outside. Even if the device is embedded, air gaps should be eliminated using the thermal paste or the glue. For the two thermistor, one attached directly to the devices and one remote or a distance from the devices. If the sensor is too far away from the devices, thermal lag time significantly reduces the accuracy of the temperature measurement. While placing the thermistor too far from the peltier devices reduces the stability. You see on the screen here we are having a thermistor mounted directly on the devices. One is far, so two is attached here, second is the remote, and one is the directly attached to the devices. That is a load, and below it we are having a heat sinker, and then thermoelectric cooler are there. So in this manner we attach the two thermistors, one is remote and second is at in the devices, on the devices. In the following figure we have see that the difference in the temperature reading taken both the thermistor. So thermistor attached to the devices reacted quickly to the change in the thermal load and recorded accurate temperature, while the remote thermistor also reacted but not so quickly, or and more importantly the readings are off by the little more than half a degree. So this difference can be very significant when accurate temperature is required. So you on the screen here we are taken here from the literature we have taken that how the both the thermistor works, the remote and the the connected thermistor with the devices. So response time of the connected are more as compared to that of the remote thermistor. So once the placement of the sensor has been chosen, then the rest of the system needs to be configured. So this include determining the base thermistor resistance, the bias current for the sensor, and the step point temperature of the load on the temperature controller we can measure. So what are the applications of the both type of NTC or PTC thermistor? The application of NTC and PTC temperature includes that temperature compensation, temperature measurement, temperature control, inrush current limiting. These are the basic application of the thermistors. Either we use the NTC or the PTC. By using this, we can measure the temperature. We can measure temperature, we can control the temperature, we can compensate the temperature, as well as we can have the inrush current limiting. And in the benefits of this NTC or PTC, NTC thermistor are rugged, reliable and stable, and they are equipped to handle extreme environmental conditions and noise immunity more as than other type of the temperature sensors. And moreover, they are compact in size. The packaging is very easy. Packaging options allow them to operate in a small or the tight spaces, thereby taking up less real estate on the printed circuit boards. So these are very compact in size and they are easy to install. Fast response time, the small dimensions allows for a quick response to change the temperature, which is important when immediate feedback is required. So these thermistors give the quick response. Moreover, they are cost effective. Not only a thermistor are less expensive than other types of temperature sensors, if the purchase of thermistors has a correct RT curve, no other calibration is necessary during the installation or over its operational life. Next important point, next application of this NTC PCC, that match point, the ability to obtain a specific resistance at a particular temperature. For this we use the thermistor. Curve match interchangeable thermistors with the accuracy of 0.1 degrees centigrade to the 0.2 degree centigrade. Now we discuss the up to now we have discussed the benefits of it. Now we will discuss in detail of these two thermistors. First we will discuss the NTC thermistor, that is a negative temperature coefficient thermistor. As you see the symbol here, we are having the minus T not minus T degree, means you can see here NTC thermistor are non-linear, and as their name suggests, their resistance decreases as the temperature increases. That is why here the notation is having the minus T degree. So a phenomena called the self-heating may affect the resistance of the NTC thermistors. When the current flows through the NTC thermistor, it absorbs the heat, causing to its temperature to rise. That is why it gives the temperature changes. Now what are the application of this? As we discussed, that it is used for the temperature measurement, compensation, temperature control, and then thermistor applications to get the more information on everything, every devices which is used to define it. And what are the benefit? It gives a fast response time, approximately plus minus 1%, accuracy. NTC thermistors have a accuracy range of 0.05 to the 0.20 degrees centigrade, and by using this we can get the more information on everything for calculating the temperature coefficient of thermistor, temperature measurement with the Wheatstone bridge. We can use this thermistor, NTC thermistor we can use. Other temperature sensors can drift over the time. In the packaging, NTC thermistors are customizable to meet the different application requirement. And in the benefits, it is a noise immunity. NTC thermistors offer the excellent immunity to electrical noise and lead resistance more so that other types of the temperature sensor. And the cost effective because of their small size and ease to production, NTC and PTC sensors prove a very economical choices, and they are used in the very. So another manufacturing process. So NTC thermistors using a mixture of the metal oxides such as manganese, nickel and copper along with the binding agent and the stabilizers. So you see here is a very small device of NTC. So NTC manufacturing process, the material is pressed into a wafer form and sintered at extreme temperatures, making the wafers ready to either disc into a small chip style thermistors or left in the form of the disc or the thermistor. You see here, this thermistor is in the form of the disc, so it is a disc thermistor. So the thermistor are available in the different NTC thermistor are available in the different configurations like disc and chip. They come configured with or without the coating, with the tinned coppered leads with quick response of the plus minus 1%. These materials are used for construction of the thermistor. There is also a broad span of the resistance values to suit every situation. Epoxy, which we will use to sandwich these materials, so epoxy dip coating and soldered between the jackets, Teflon PVC wires we use. Their small dimensions allows for easy installation and they can be point or the curve matched. Moreover, the glass encapsulation is there to prevent from the outside moisture or outside waterproofing will be done. An excellent choice when dealing with extreme environmental conditions. Configurations include radial leaded or the axial leaded, and pro assemblies available in the variety of housing depending on the application requirements. Surface mount also there. Configuration options include bulk, tape and reel, two-sided or wrap around. And with palladium silver terminations made with the nickel barriers, these thermistors work great in precision circuit. So these are the main points for the NTC thermistors. Now what are the output that we can get and what are the parameters used in the NTC thermistor? First is the dissipation constant, that is DC or the delta D. The dissipation constant is the ratio normally expressed in the milliwatt per degree, that is milliwatt per degree centigrade at a specified ambient temperature of a change in the power dissipation in the thermistor to resultant body temperature changes. So in the NTC thermistor, the next is the material constant, means the beta, which is also play a very important role in the construction or in the output of the thermistor. So the material constant of the NTC thermistor is a measure of its resistance at one temperature compared to its resistance at the different temperature. Its value may be calculated by a formula, as we know that beta is equal to, already we have discussed this formula, and then we can express the degree or the output by using this. Maximum power rating, the maximum power rating of the thermistor is the maximum power expressed in the watt or the milliwatt, which is thermistors will dissipate for an extended period of the time with acceptable stability of its characteristics. So these are the basic points in the NTC. Further we will discuss this point, and another point is the temperature tolerance. This type of the thermistor, this is one of the parameter which is very important, that the temperature tolerance equates to how much variation in the degree centigrade we can expect from a thermistor at a particular temperature for a particular device. So temperature tolerance is the one of the parameter. Temperature coefficient of the resistance, that defined by the alpha, that is defined the absorbability. So the ratio of the specified temperature T of the rate of change of zero power resistance with the temperature to the zero power resistance of the thermistor. So the temperature coefficient commonly expressed in the percentage per degree, that is percentage per degree centigrade. So that define the temperature coefficient. Next is the temperature tolerance, that how much temperature tolerance means that define the variation in the degree centigrade. How much can thermistor at a particular temperature. Temperature tolerance equates to how much variation in the degree centigrade we can expect from the thermistor at a different temperature or in the different devices. Thermal time constant, it is also thermistor changes the 63.2% total difference between the initial and the final body temperature. Thank you very much.